positive integers are the numbers 1, 2, 3, 4, etc. And I'm going to prove to you that every positive number is interesting. A mathematical proof of this theorem. What is it going to be? You're going to find out in a minute. So let's do it. What we're going to do is we're going to assume for a contradiction that there is a boring positive integer. Okay, so assume for a contradiction that there is a boring positive integer. Boring being the opposite of interesting. Okay, I'm being very rigorous here. Assume that there is a boring positive integer. Now collect all the boring positive integers. Okay, so we know there's one. We're assuming there is one. For a contradiction, collect all of them. Okay, that's going to be a non-empty set of positive integers. Okay, so let S equal to the set of all boring positive integers. By that I just mean we're collecting all the boring positive integers. We know there's at least one by our assumption at the beginning of the proof, and we know that S is therefore non-empty. Now it's a famous principle, the well-ordering principle for the natural numbers. The positive integers or the natural numbers are 1, 2, 3, etc. And the well-ordering principle tells us that any non-empty set of positive integers has a least element. Okay, so that's going to be the subject of another video, and it's going to pop up on the screen when it's available. Okay, so at the end of this video you're going to see that, but it's intuitively clear. You can always find a smallest element for each non-empty set, and so therefore the set S is going to have a smallest element. It's going to be a smallest boring positive integer. Okay, so therefore there exists a smallest boring positive integer n, and we're almost at the end of the proof. Okay, this is our smallest boring positive integer. Well, if it's the smallest boring positive integer, then it is interesting, because if it's the smallest, then by definition of being the smallest boring positive integer, it must be an interesting number, right? That's a contradiction though, because we assume that the set S was only consisting of boring positive integers, and so this is actually not a boring positive integer. It's the smallest one. It's not boring, it's interesting. That's a contradiction because it's not in S. So therefore our original hypothesis was false, and every positive integer is interesting, and that is the end of the proof, QED. Let me know what you think in the comments down below, and when it's uploaded you're going to see a proof or a discussion here of the well-ordering principle for the natural numbers, which is super beautiful. I'll see you in that video, but until it pops up you'll see another video there which will also be super fun, another math proof. Check that out, and I'm going to see you in the next video. Wish you all the best and see you in that video.